Before telescopes, before rockets, before humanity even understood what stars were, there was already something quietly shaping the universe. Numbers. Not just the numbers humans write on paper, but patterns, hidden structures that seem to guide everything in existence. The motion of planets, the birth of stars, the expansion of the universe itself, all of it can be described with mathematical equations. But here's the strange part. Why should the universe follow mathematics at all? Why should reality obey logic that can be written in symbols and formulas created by human minds? Tonight, we're going to explore one of the deepest mysteries in science: why the universe appears to run on mathematical laws, and what that might reveal about the nature of reality itself. Because by the end of this journey, the question may no longer be why mathematics describes the universe. The real question might be, is the universe itself made of mathematics? Look up at the night sky for a moment. Planets move in predictable paths, stars shine according to measurable laws, and light itself travels in patterns that scientists can write as equations. It's almost as if the universe is following a script written in numbers, and that raises a strange and fascinating question. Why should reality obey mathematics at all? After all, mathematics is something humans write down with symbols on paper, yet somehow those symbols describe the motion of galaxies and the dance of atoms. It's as though the cosmos understands a language we only recently learned to read. Consider something simple: the path of a thrown ball. From a baseball in a stadium to a comet moving around the sun, the motion follows the same mathematical curve. The same equations that describe a child tossing a ball can also describe the orbit of planets. Different scales, same hidden pattern. This strange connection appears everywhere scientists look. Gravity, motion, light, energy. All of them behave in ways that can be captured with numbers and formulas. It's almost as if the universe prefers order over chaos, as though reality itself is built upon invisible rules. But here's where the mystery deepens. If mathematics truly describes the universe so perfectly, then those patterns must be appearing everywhere around us. Not just in distant galaxies, but in the everyday workings of nature. So the next step is to look closer and see where these patterns begin to reveal themselves. If someone could step outside the Earth and watch the solar system from above, the first thing they'd notice is the rhythm. Planets circle the sun in graceful loops, each following a path that repeats again and again. It's not random wandering through space. It's more like a perfectly choreographed cosmic dance. For centuries, astronomers noticed that these motions weren't chaotic at all. Planets returned to the same places in the sky at predictable times, almost like clockwork. By measuring their movements carefully, scientists discovered something remarkable. Their paths could be described using precise mathematical equations. Imagine a spinning top on a table. As it spins, its motion isn't random. It follows patterns determined by forces and balance. In a similar way, planets move through space following the invisible pull of gravity, and that pull behaves in ways mathematics can describe with astonishing accuracy. The same idea works for stars as well. Astronomers can estimate how long a star will live simply by measuring its mass and brightness. They can even predict how stars will change over millions or billions of years. Again and again, nature seems to follow mathematical relationships. Even the expansion of the universe itself obeys these patterns. Galaxies drift away from one another at speeds that can be calculated using mathematical models. It's as if the entire cosmos is unfolding according to hidden rules. But to understand just how deep those rules go, we have to zoom much closer, far beyond planets and stars. Now imagine shrinking, smaller than a grain of sand, smaller than a cell, smaller even than an atom. At this tiny scale, reality begins to behave in ways that seem strange and almost magical. Particles flicker in and out of existence, energy jumps in discrete steps, and certainty fades into probability. Yet even here, in the strange world of quantum physics, mathematics still rules. Electrons orbit atomic nuclei, but not like planets circling the sun. Instead, they exist as shimmering clouds of probability, described by mathematical wave functions. Scientists can't always predict exactly where a particle will appear, but astonishingly, they can calculate the chances with incredible precision. It's a bit like predicting the patterns of ocean waves during a storm. No one can track every drop of water, yet equations can describe how the waves rise and fall. In the same way, quantum mathematics maps the behavior of the tiniest pieces of reality. Even uncertainty itself follows mathematical rules. These equations reveal patterns that repeat across the entire universe. The same quantum laws shaping atoms inside your body also govern the atoms inside distant stars. No matter where scientists look, from laboratory experiments to interstellar clouds, the same relationships appear again and again. It's as though the universe is built from mathematical blueprints at its deepest level. But the story doesn't stay confined to the microscopic world. Those tiny mathematical rules scale upward, influencing objects millions of kilometers wide. The same logic shaping particles inside atoms also shapes the motion of entire planets. So the next step is to zoom back out, toward the grand architecture of planetary systems. Now the view begins to expand again. From the microscopic dance of particles, the scene rises outward to entire worlds moving through space. Planets glide around their stars in vast, sweeping paths that repeat over and over. And once again, mathematics quietly governs every step of the motion. Imagine an ice skater spinning on a frozen lake. When the skater pulls their arms inward, their rotation speeds up instantly. This isn't magic. It's a predictable physical rule. And the same mathematical principle applies to planets, moons, and even entire star systems. Centuries ago, scientists discovered that planetary orbits follow simple geometric patterns. Instead of perfect circles, planets move along slightly stretched paths called ellipses. With just a few equations, astronomers can calculate where a planet will be years, or even centuries, into the future. The heavens move with a reliability that almost feels mechanical. Gravity is the invisible force guiding this cosmic choreography. Every planet constantly falls toward its star, yet its forward motion keeps it from crashing inward. The result is a graceful orbital path, like a stone spinning at the end of a string. Mathematics captures this balance perfectly. Because of these equations, scientists can predict solar eclipses thousands of years ahead. They can calculate the precise paths of comets returning after centuries in deep space. And they can even guide spacecraft across billions of kilometers using the same laws. Which raises an exciting question. How exactly do humans use these mathematical patterns to explore the cosmos? Once scientists realized that the universe follows mathematical rules, something remarkable happened. Those same equations didn't just explain the cosmos. They became tools for navigating it. Suddenly, mathematics wasn't only about understanding space. It became the key to traveling through it. Imagine trying to throw a ball into a moving basket from kilometers away. Now imagine the basket is a planet moving tens of thousands of kilometers per hour. That's essentially what engineers must do when sending spacecraft across the solar system. Without mathematics, hitting that target would be impossible. Before a rocket ever leaves the ground, scientists calculate its entire journey. They determine how gravity from Earth, the Moon, and the Sun will influence its path. They map invisible curves through space called trajectories, and every part of that journey is guided by equations. Sometimes spacecraft even use something called a gravitational slingshot. By flying close to a planet, a spacecraft can steal a tiny bit of the planet's orbital energy. It's similar to a skateboarder gaining speed by swinging around a pole. Mathematics allows engineers to calculate these delicate maneuvers with incredible precision. Because of these calculations, humanity has sent probes to Saturn, Pluto, and beyond. Machines built on Earth now travel through the darkness between planets. Every course correction, every orbital insertion, every landing attempt follows mathematical predictions, which leads to a deeper realization. Mathematics doesn't just help us explore the universe. It seems to be the very language the universe itself speaks. At the heart of modern science lies a simple but powerful idea. The laws of physics can be written as mathematical relationships. Instead of describing nature with long paragraphs, scientists describe it with equations, and those equations reveal how the universe behaves. Take motion, for example. When an object moves, its speed, position, and acceleration are connected through mathematical rules. The same relationships describe a car driving down a highway and a planet orbiting a star. Different situations, yet the same underlying logic. Energy follows mathematical patterns as well. When energy changes form, from heat to motion, or from light to electricity, it obeys precise conservation laws. It's a bit like money moving between bank accounts. The numbers may shift, but the total always balances. Even forces such as gravity and electromagnetism are expressed through equations. These formulas show how objects influence one another across space. They tell scientists how strongly two masses attract or how charged particles interact. Nature, it seems, keeps perfect mathematical records. This is why mathematics works so well in science. It acts like a universal language, clear, precise, and understood everywhere in the cosmos. From atoms to galaxies, the same mathematical structures appear again and again, and those structures played a crucial role long before Earth even existed, during the birth of our solar system itself. Long before Earth had oceans, mountains, or life, the solar system began as something far simpler. A vast cloud of gas and dust drifted through space, slowly rotating in the darkness. At first glance, it might have looked chaotic, particles moving in every direction. But even inside that enormous cloud, mathematical laws were quietly shaping its destiny. Gravity began to pull the cloud inward. As the material collapsed, the entire cloud started spinning faster and faster. It's the same effect you see when an ice skater pulls their arms toward their body and suddenly spins faster. The laws of motion demanded that the rotation speed increase as the cloud shrank. Soon the collapsing cloud flattened into a giant spinning disk. Most of the material gathered at the center, forming the young sun. Meanwhile, the remaining dust and gas circled the newborn star in predictable orbital paths. Once again, mathematics guided how matter organized itself. Inside that disk, small grains of dust collided and stuck together. Tiny clumps grew into rocks, rocks into mountain-sized bodies, and eventually into planets. Each collision followed the same rules of motion and gravity described by equations. Even the chaotic process of planetary formation unfolded within mathematical boundaries. Over millions of years, those growing worlds settled into stable orbits around the Sun. Mercury, Venus, Earth, and the other planets took their places in a balanced cosmic system. The solar system became a giant clockwork of moving worlds. And that stable mathematical order would later create the conditions necessary for something extraordinary to appear on Earth. Now consider something easy to overlook: the reliability of nature on Earth. The sun rises each morning, seasons arrive in steady cycles, and gravity pulls objects toward the ground every single time. These patterns feel ordinary because we experience them every day. But behind that stability lies the quiet consistency of mathematical laws. Earth orbits the sun in a nearly perfect rhythm. Our planet completes one full journey every year, giving rise to the familiar cycle of seasons. Tilted slightly on its axis, Earth experiences shifting sunlight across its surface. The mathematics of orbital motion makes this rhythm predictable and stable. That stability allows chemistry to work reliably. Atoms bond into molecules according to precise physical rules. Water forms with the same structure, whether it's in a cloud, an ocean, or a living cell. Because these laws never suddenly change, complex chemistry can unfold over long periods of time. Biology depends on this reliability as well. Life is built from intricate molecular machines, proteins, DNA, and countless chemical reactions. Each reaction follows predictable physical laws. Without that consistency, the delicate processes of life would collapse into chaos. In a sense, life itself is built on a foundation of mathematical stability. From the rhythms of our heartbeat to the cycles of ecosystems, patterns repeat again and again. Yet Earth is only a tiny stage where these patterns play out. The same mathematical order stretches far beyond our planet, shaping the grand structures of entire galaxies. Now the perspective stretches far beyond our solar system. Instead of a handful of planets orbiting a single star, we begin to see entire galaxies filled with hundreds of billions of stars. These enormous structures drift through space like glowing islands in a cosmic ocean. Yet even at this staggering scale, mathematics still quietly governs the motion. Inside a galaxy, stars move in vast circular paths around the galactic center. Our own sun is part of this grand motion, orbiting the center of the Milky Way. It takes roughly 230 million years to complete just one trip around the galaxy. Even this enormous journey follows the same gravitational laws that guide planets around stars. Astronomers use mathematical models to track how these stellar systems evolve. By measuring the speeds and positions of stars, they can map the invisible gravitational structure of a galaxy. These calculations reveal something surprising. Galaxies behave as if they contain far more matter than we can actually see. This discovery led scientists to propose the existence of dark matter. Though invisible, its gravitational influence shapes the rotation of galaxies and the motion of galaxy clusters. Mathematical equations reveal its presence even though telescopes cannot directly observe it. Once again, numbers uncover hidden layers of the universe. Galaxies themselves also interact and merge over billions of years. Astronomers can simulate these colossal events using mathematical models. They watch virtual galaxies collide, twist, and reshape themselves in slow cosmic dances. And those simulations hint at something even more profound, patterns that stretch back to the very birth of the universe itself. To understand why mathematics describes the universe so well, scientists often look back to the very beginning of everything. Modern cosmology suggests that the universe began in an extraordinary event known as the Big Bang. Nearly 14 billion years ago, space itself began expanding from an incredibly hot and dense state. And from the very first moments, that expansion followed mathematical rules. Astronomers today can measure how fast galaxies move away from one another. These observations reveal that the universe is still expanding. Using equations derived from physics, scientists can rewind that expansion backward in time, like tracing ripples in a pond back to the moment a stone was dropped. Those same equations also explain how matter gradually gathered into structures. Tiny fluctuations in the early universe grew under the influence of gravity. Over billions of years, these slight differences in density formed galaxies, clusters, and vast cosmic filaments. Mathematics allows scientists to simulate this entire transformation. Computer models now recreate the growth of the universe on enormous scales. Starting from simple mathematical conditions, these simulations produce structures that closely resemble the real cosmos. Galaxies form, cluster, and weave together into the vast cosmic web we observe today. It's almost as if the universe unfolded according to a set of cosmic instructions. Yet this realization raises a deeper question. If mathematics can describe the universe from its earliest moments to the present day, what does that actually mean? Are these equations simply human tools for understanding nature? Or could mathematics itself be woven into the very fabric of reality? At this point in the journey, a strange realization begins to emerge. From the smallest quantum particles to the motion of galaxies, mathematics seems to describe everything. The universe behaves as if it follows a hidden logical structure, almost like a vast cosmic system running on elegant rules. But this raises a question that has fascinated scientists and philosophers for centuries. Did humans invent mathematics, or did we discover it? If mathematics were merely a human invention, it would be surprising that the universe follows it so perfectly. Yet the equations continue to predict nature with astonishing accuracy. Think of mathematics like a map. A map doesn't create mountains or rivers. It simply reveals where they already are. In the same way, equations may be showing us the underlying patterns woven into reality itself, patterns that existed long before humans ever appeared. The deeper scientists explore the universe, the more these patterns appear. From the spirals of galaxies to the vibrations of quantum fields, mathematical relationships keep appearing. It's as though the cosmos is built upon a framework of logic and symmetry, a structure that quietly governs how everything unfolds. And perhaps that is one of the most remarkable discoveries humanity has ever made. With nothing more than curiosity, observation, and numbers, humans can uncover the rules of the cosmos. Tiny minds on a small planet can decode the logic of an entire universe. Which leaves us with one final thought. Maybe mathematics is not just a tool for understanding reality, but a fundamental part of reality itself.